I joined work with these cool people, Holden and Andre. And yeah, it's about when MCMC meets variational methods, and the question is what happens when that happens. Okay, so hopefully many of you guys went to the tutorials, which were very cool, and you heard about the Ising model and sampling and lots of cool things, but I'll remind you just in case you forgot that you're so excited about this. So this is the model. So it's a class of models that have two parameters. So one parameter is the matrix J, which describes the interaction. So here X is a vector, it's on the hypercube, so you can imagine it's like n people, and they're deciding whether to vote for political party A or political party B. And this matrix J tells you, well, people are friends or they're enemies, so they like to align their opinion, or they have enemies, they really want to vote for the opposite party from their enemy. So you can imagine this is a very realistic model of social interaction. And there's a vector H, which is the biased or external field, which is just more like your personal opinion, okay? And so this is a general class of models. Not only is it useful for social networks, but also apparently for magnetism, spin glasses, Bayesian statistics, and so on, okay? And maybe if you don't like those kinds of things, you like maximum entropy distribution. So this is one of the most important, famous maximum entropy distributions. So it's a so-called exponential family. So it's exactly an analog of a Gaussian if I'm constraining to the hypercube instead of to continuous space, okay? So that's the model. You probably saw it before this week, okay? And so we want to do sampling, okay? But I thought I should defend, why am I talking about sampling in the computational complexity of statistical inference workshops? Okay, so let me defend it, even if you don't care. So it has many connections. So one reason is that, like I just said, many Bayesian problems, you think about it real hard, you realize it's just an Ising model. So here's one example, which you might find interesting or not interesting, but maybe you don't like Ising model, but you like posterior sampling. Well, I can give you this task where I have a latent vector x, which is uniform on the hypercube. And then I tell you not x, but I give you a noisy observation. So it's x plus normal 0 sigma for some covariance matrix sigma and some y. And if you think, or you just do a calculation, you realize every Ising model is of this form. So that's actually, if you don't like Ising models, but you do like Bayesian statistics, just always pretend it's that, okay? And another good one that was kind of mentioned in Salil's talk is stochastic block model. It's easy, or you just sit down, use a calculation, you realize the posterior in that model is the Ising model, okay? And another reason, which you don't like Bayesian statistics, but you like normal statistics, then you want to estimate the truth from the data. So you have samples from an Ising model, and you want to estimate J and H. How will you do that? Well, you want to do the best possible. The best possible would be maximum likelihood estimation. So this figure just represents, like you come up with any other algorithm, in the limit as the number of samples go to infinity, this is just some alternative score matching. It's just not as good as maximum likelihood, right? And that's kind of because of the fundamental theorems of Lecam and others, okay? Okay, so that's all I wanted to say about statistical inference. Let's forget about that, and let's just talk about sampling. Okay, so how do we do sampling? Maybe we use a Gibbs sampler. So you start with some initial configuration on the hypercube, and then for a bunch of times, you pick a random coordinate and you resample it, right? So this is the Gibbs sampler, and this is just running in a simple example, okay? And probably like we saw in Kui's talk, it's important to understand whether this actually works, okay? So it may not work, it may take exponential time to mix, and some of the models are even hard to sample from, so not only does this process not work, but no algorithm can sample from them, right? Okay? And so with that, I want to talk a bit more about the theoretical aspects of Markov chains, right? And so we'll start with this example, which I think we also kind of saw before, but it's a really helpful example. So this is a distribution. This corresponds to a rank 1 interaction matrix. And beta is this parameter, which we call the inverse temperature, and just corresponds to the strengths of interactions in the model. If beta is small, then by a result of debrution, this thing will mix, the Glauber will mix quickly. And when beta becomes large, this is the picture. There's 2 clusters in the distribution. The Gibbs sampler gets stuck in one cluster, and it's not able to get to the other one. So the runtime of Gibbs sampling would be exponential, because that's how long you need to wait to get a real sample. Okay? So hopefully that was reviewed. But yeah, I realize I'm going fast over the preliminaries, so please feel free to ask any questions. And let me tell you, well, what happened in the previous example is when the beta is small, it mixes. That's quite a general fact. And it's like some self-promotion, but we proved this nice result that if J is small and this operator norm, then the Gibbs sampler mixes rapidly. But that's just one of many, many results saying if j is small, then things are good, okay? On the other hand, we saw in the previous slide, if j is big, no matter how hard you try to work to prove a theorem, it's just not true that the given sampler works. It doesn't work, so you cannot prove that it works. So with that, well, what else can we do? Something else we can do is we can do this thing called variational inference, which is pretty cool. So variational inference is built on this idea that we'll approximate the world, which is like complicated, by something else, which is simpler. And actually, this is really, really good for this Curie-Weiss model. So in this model, there's kind of two clusters. There's one cluster where everyone is mostly minus, and one cluster where everyone is mostly plus. And what you can do is you can formally prove that this distribution is kind of well approximated by a mixture of two product measures. One product measure is the mostly plus state, and one product measure is the mostly minus state. And again, like if you went to Will's talk, this is kind of like a slightly less sophisticated idea than the cluster expansion, but it's doing something similar. It's saying like it's mostly plus, but there's some deviation. Okay, so this is a pretty good description of that particular model. And it turns out this is actually a very general phenomena. Okay, so what's going on? So there's a lot of works here, but I just cited two. What they showed is that like that's not just something that happens in that one example, which is really easy to solve, but it's actually something that happens in a very general situation. Okay, and this is kind of the picture. You take any Ising model with a low-rank interaction matrix. It's basically a mixture of product measures. Okay, but what does it mean when I say basically? Okay, so this is essentially what their theorem says. If the rank is sublinear, then the Ising model is a mixture of 2 to the little o of n product measures. Every distribution is a mixture of 2 to the n product measures. So this is 2 to the little of n is a non-trivial. There's some equation which tells you the means. And when I say that this is like basically the same thing, it's really that it's a sublinear approximation in Wasserstein distance. So in some sense, that's quite good. In other senses, it's not so good. I mean, if you really look into the clusters, they're not product measures. That's just the reality. So that's why this is only an approximation. And also, this is not constructive, except by the end of the talk, I would tell you how to make it constructive. But this is really just a structural fact, okay? And so that kind of leaves us with the following situation. Variational inference is really good. It makes sense in the multimodal case. And when you look in the world, there are many distributions which are multimodal, right? So that's good. But bad is really only an approximation. It's kind of a crude approximation. There are algorithms, but they don't really have good guarantees. Or there's structural results, which are very beautiful mathematically, but they're not algorithmic. On the other hand, we have Markov chains, which are really good. When it works, it really samples from the true distribution. It's not approximation. But it obviously fails in lots of cases, okay? And so what we want to do is we want to combine the two, right? And so this is the theorem. What we did is we found that there's a Markov chain which can sample from this whole class of models. But I need to explain a bit about the runtime, okay? So the runtime is going to depend on the spectrum of the matrix J. And basically what you need to do is you assume most of the eigenvalues live in an interval of size 1. And that there are a few outliers. Okay, so these are just eigenvalues that are bigger than size 1. And what the runtime depends on is the number of these spectral outliers. Okay, and the runtime is basically n to the number of outliers. And you might think that that's good or that's bad, but it's, if you went to Virginia's talk, there's this exponential time hypothesis, so you cannot really do better than this, actually. Okay, so for the worst case model with that many eigenvalues, you do basically need that runtime.
So are you sampling from distribution that's close on TV or Wasserstein?
We're really sampling, so it's like, yeah.
On TV.
Yeah, you can get like 2 to the minus n TV, okay. Yeah. Right. Yeah. And another thing is the negative eigenvalues actually need to be somewhat bounded in size, otherwise you run into some NP hardness. So this actually is pretty easy to explain, but I'm not going to explain for reasons of time, okay? So that's kind of what the result is. So it's like we can actually sample when there's all these spectral outliers which lead to multimodality. And so now let me tell you just a bit about the proof. I'm not going to go into all the details, but hopefully give you a taste. Okay, so the key is kind of, instead of decomposing the Ising model into a mixture of product measures, which you can only go so far that way, we're going to decompose into a mixture of high-temperature Ising models, okay? And these are just going to be models which have a small operator norm of the interactions, which are models which we therefore know how to sample from with MCMC. And unlike the old mixture of product measure decomposition, I'm going to show you how to do it constructively, so with an algorithm. And this decomposition is very accurate. So that's going to enable the total variation sampling that Ankur was asking about. So just the picture is the same picture, but now we have Ising models. and yeah, enable polynomial time sampling of the real distribution. So in some sense, it's a big step forward. Okay, and so the idea is we don't like to have the spectral outliers, so we'll discover a way to delete them. And there's one method to delete the positive ones and one method to delete the negative ones, and I'll tell you a bit about these. So how can we kill the positive ones? Well, what we can do, we can write the matrix. This J prime has all the small eigenvalues, and JLR has all the big ones. And we want to get rid of the big ones. And what we'll do is we'll construct exactly a mixture distribution over models which only have J prime, so they have no large eigenvalues. So the same picture as before, such that the original distribution is basically this mixture. So Q is the mixture weights. Okay, and how can we do that? It seems like it might be hard, but it's actually not that hard. And so what do? You just use this fun fact. So what's going on here? This just is actually some expression of the fact that like a Gaussian, its Fourier transform is also a Gaussian, or you could just compute this integral. It's pretty easy. And you'll see that this is a true fact. So it says if you have e to a quadratic with a PSD matrix, then it can be written as this kind of integral. Okay, so just accept that, hopefully. So it's just also it's just a moment generating function of Gaussian. Okay, so if you are willing to accept that, which is just a calculus thing, then what do? Well, this is really good because you get rid of the J low rank term by applying this formula. So here's the original distribution. Then we can split J into J prime and J low rank. We use this formula to replace the low rank term by this guy, which has a linear thing in the exponent. So just literally plugging this in, we get this. And then we're really happy because this starts to look like a high temperature Ising model. And actually, formally, this is a high temperature Ising model, but you need to renormalize by the normalizing constant. And so I think I went over this a little bit fast, but like just by applying this formula, you actually get such a decomposition. So actually, it's not so bad, yes.
Okay, that was really fast.
Oh, okay. Yeah, sorry. It's just,
It's okay, no, I just want to ask some questions.
Yeah.
So is there some, can I interpret, is there like a sampling procedure? Maybe you're going to tell me in a second. Like, how do it sounds like there's, like I draw the new H vector from some Gaussian that I know how to sample from, and then that gives me a new Ising model.
Yeah. So what you were saying is almost right. So if there was no Z, J prime, blah, 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 so okay, this is a normalizing constant. So if this was 1, then it would just be a Gaussian. So that's not the correct thing to do. So
Wait,
yeah.
when they say it would be a Gaussian, it is
The new external field would be some type of Gaussian. Yeah, but that won't be right because you need to take account of these normalizing constants. Otherwise, it would be a Gaussian. Oh, this is, okay, I'm going fast. So the point is there's few spectral outliers. So JLR is low rank, so this is a low dimensional integral. So I can actually compute integrals in low dimension, right? That's fine.
So
Okay.
The integral you're going to actually compute.
Yeah, we're actually going to compute it. We're gonna do it. Yeah.
To do some sampling.
We're going to do Riemann integral. Yeah.
I see. So that part you compute, and then you just want to do the sampling on inside.
Yeah, exactly right.
Okay, so basically you're saying there's some kind of low rank perturbation of a Gaussian that I'm gonna like it's low rank in the sense that you're gonna compute the normalizing constant by doing an integral over a small dimensional.
Yeah, we're doing it's a low dimensional distribution. We just can explicitly sample from it.
From this distribution in some kind of brute force fashion.
Yeah, right. Yeah.
And then you say, okay, hey, now I have a sample from this distribution. That's my new external field.
Yeah, exactly. Yeah.
And now I've got a low temperature Ising model with an external field running Gibbs sampling.
Yeah, right. Yeah, you understand it 100%. Wow. Okay. So that was the easy part. Sorry.
Just the integral thing. So
Yeah.
you're going to pay some price that's like what, exponential in the lowering?
Yeah, exactly. And that's
That was
the
end of the low rank.
n to the number of outliers, and it's required because of the exponential time hypothesis. Yeah. Okay. So I really just want to give a taste. I realize I'm going too fast, but.
A couple slides ago, you had this picture of like a mixture of like 2 to the r different
Yeah, right.
Gaussians, and here you kind of have a continuous mixture.
Yeah, so that's why you have to use Riemann integral, and then you'll get a discrete
So
mixture.
is there an easy way to see that this recovers like 2 to the r things?
Basically, the dimension is r, and then when you do the Riemann integral, you get like n to the r. That's basically what happens. Yeah. Okay. Yeah. Thanks for all the questions. Okay. So unfortunately, that was the easier part. So this is the more difficult part, which I apologize in advance because I think it's not going to make any sense. But hopefully, you'll see this and you'll be like, "Wow, it's so cool!" And you'll read the paper where we, try to explain it very carefully. Okay, so here's the trick. So I have my matrix J, and I split into PSD and negative definite parts. Okay, and what I'm going to do, well, we know machine learning stochastic gradient descent is very good. So what we're going to do is we're going to run stochastic gradient descent, but on this function. And then you're probably thinking like, whoa, what is this function? Like, it kind of looks weird. It doesn't make much sense. So now let me try to explain where it came from. So what you do is you postulate that J minus X, so this is the negative definite part of J, and X is a sample from the model. We postulate that this concentrates, and this is actually going to let us derive this function G, okay? So let's suppose that J minus X concentrates. Then I have XJX, so this is the exponent in the Ising model. We can split it into the J plus and J minus parts. And the J minus part, it goes from being quadratic to linear because we approximate X by mu. So that's the key, is to assume that there's concentration, okay? And that's an optimistic assumption, but it turns to work out. And this will be really good because then one Ising model, which has large negative eigenvalues, can be approximated by another one, whereas the negative eigenvalues are gone, but I have a new external field, okay? Yeah, so.
What was the connection? Okay.
Yeah.
What was the connection between the SGD on?
Oh, I didn't finish explaining. Okay, yeah, sorry. So, okay, first I'm just saying, well, let's suppose this is a nice world where J minus X concentrates. Then this model is close to this model. Okay, and then what that means is J minus mu, well, this is like approximately the mean of J minus X under the real world. But this real world is approximately this other distribution, so we have this approximation. And this is just the Ising model without the negative eigenvalues and with a new external field.
Wait, so why does J minus X concentrate well enough?
No. So this is it's a physics, right? So we are assuming the world is nice. We're going to get a formula, and then you have to actually do the math. So I'm not going to explain the actual math.
Okay.
Is it like because it's kind of low dimensional or something?
No, because negative eigenvalues sort of should only make things better. That's the intuition. Yeah, but that's not how the proof exactly works.
Okay, so I mean, like, if J minus were like the whole, part of the picture of like what was happening, then somehow you would hope that X concentrates so that,
Yes.
basically that you're sort of deciding who disagrees with who, right?
Yeah.
But sort of as J minus gets close to this boundary of your small part, I mean, yeah.
Okay, I apologize. This is, yes, I appreciate it. It's sketchy. So this is all useless in the sense that this is just letting me derive G. And once I have G, I actually need to do the proof, which is not going to work exactly like this. So,
What is G supposed to
okay, so let me tell you. Let me tell you. So this whole calculation, which, okay, what the heck? But actually, if you look at J minus mu and you're like, okay, I want this to equal this, then that's exactly gradient G equals 0. And that's actually how we came up with G. So there's probably no way to come up with G except to make this heuristic argument. Okay, so that's.
Is it actually, like you can prove something with G, but is it actually the case that this thing concentrates? Probably not.
I think it does end up to concentrate. Okay, but it's not the correct order of. Yeah, so we first need to guess the right equation. So like if we were at like Michael's talk, there's like this tap equation for SK model. So this is just like some other kind of fixed point equation. We really need to guess this equation, and then once you guess the equation, you can prove everything. But this is the only way to explain, I think, where the equation comes from.
The equation
Yeah.
is the thing whose fixed point will be the new external.
Yes, exactly right. Yeah,
J minus isn't somehow small in
it's like low rank, but it's not.
It's
And
not smaller
it's
than
it's the operator norm is upper bounded by say a large constant like 100. Yeah.
But you can't give us any. You're not willing to give us any intuition about why it's concentrated.
No, imagine if you have a Gaussian and.
Is it like negative correlation or negative?
Yeah, it's like, it's not negative correlation, but imagine you have a Gaussian and as you take the variance of the Gaussian to 0 and you look at the PDF, it looks like e to the negative x transpose sigma inverse x. So as Gaussians concentrate more and more, you get more and more very large negative eigenvalues of the matrix negative sigma inverse. So that's why we think that negative eigenvalues only make things concentrate. But yeah, that's obviously not a legitimate explanation, but that's intuition. Yeah, okay.
I like that.
Yeah, okay, yeah, I apologize. So there's a proof, it's not a proof, it's just a heuristic argument, but fact is that it works. Okay, so G has a critical point, at any critical point, this approximation is true. Okay, and what does it mean it's true? You can sample from this guy, and you can use rejection sampling, and you can get this guy. Okay, so there's a lot of stuff swept under the rug, but if you are willing to accept this function into your life, actually all the arguments are pretty easy. Okay, so the mystery is why this is the function. But hopefully you found this a very convincing argument why this is the function. Okay, and so that's the algorithm, and like Sam was kind of saying, what's going on? We have this integral representation, and we just need to do it all. Okay, so I just wrote down all the steps, not very exciting. So there's an integral. We use a Riemann integration. You need to compute this mu b. This is the thing from the previous slide. That can be done with stochastic gradient descent. And then you have this p, j prime, blah, blah, blah. That can be sampled from by Glauber. And finally, there are some approximations, so you have to do rejection sampling. So that's the whole algorithm. It's a little bit complicated, but basically just follow from this formula. Then you want to make it more complicated. This only gets Pauli 1 over epsilon runtime is the total variation error epsilon. But we can make it log 1 over epsilon by making things much more complicated with simulated tempering. And I won't explain that because it's more complicated. Okay? But basically, that's the algorithm. Okay? So if you're willing to accept all the previous slides, this is what you get. Okay? And now I thought I'll just finish by showing you an application of this. So you can obviously apply it to Curie-Weiss, but maybe that's kind of easy, and then you think that this theorem is not so good. So let me show you a more complicated application. So the application is to dense max cut. So this is a problem. It's a very classic one. You have an adjacency matrix of a graph, and the graph has n squared edges. And your goal is to find the maximum cut. So you want to split the vertices into two sets so that there are as many edges crossing between the two sets as possible. Okay? And this is a famous problem, and it admits a polynomial time approximation scheme. So you can solve this optimization up to a factor 1 plus or minus epsilon. Okay? There's actually a lot of algorithms for this, and now I'll tell you another one. So what we do is we want to solve this. Let's use statistical physics approach. Okay, so this is the objective, but for a reason that I won't explain, I just I rescaled the objective by 1 over n. You just have to do this. It's not super exciting. And then what we want to do is instead of looking at one optimizer, let's look like this whole distribution over all approximate optimizers. And that just means you look at the objective and you put this into the exponent, and then you put this beta, which is the inverse temperature. So as beta becomes very big, this distribution basically just concentrates on the maximizers, but we'll look at this for every beta. And here's two exercises. So one is that if you make beta large, this will really concentrate on optimizers. So if you look at the expected value of the objective for a sample from this model, it becomes very close to opt. Okay? And second exercise is that this matrix satisfies the assumptions of our theorem. So it has few large eigenvalues. This is just a calculation. Okay? So if we are willing to accept those two things, we get the following corollary. For any beta that is non-positive, you can sample from the Gibbs measure in time n to the order beta squared. And this yields a 1 plus 1 over beta approximation to dense max cut. So basically, you get 1 plus epsilon in times n to the 1 over epsilon squared. That's actually the same runtime as the original polynomial time approximation scheme for this problem. But now we kind of did better than them because not only can we get one optimizer, we can get all of them. Okay? So that's kind of cool. Some things that are going on that seem interesting. So if you went to Quique's talk, maybe he mentioned that there's computational phase transitions where for small temperatures things are possible. For large temperatures, they're not. But here, it's actually possible at all temperatures. And actually, another thing that's interesting here is the sampling is somehow easier than the optimization, even though many times it's the reverse. Okay?
Sorry, what does that mean? Sampling is easier than optimization here?
In many cases, if you look at the optimization problem, it's possible, but we don't know how to do the sampling analogs.
Sure.
But here, it's the opposite. The optimization, exact optimization is NP hard, but we can sample. Yeah, that's all I'm saying.
But
that's
the
not.
exact optimization would correspond to a different beta.
Yeah, sure. Okay. It's not a deep thing. I'm saying. Okay.
So the fact that you have few negative eigenvalues, this is just because you did the scaling by 1 over n?
Yeah. So the 1 over n is needed so that you'll get this 1 plus epsilon approximation.
Why is it that that's also the magic thing that popped out with the negative eigenvalues?
Because okay, so we need to rescale the objective to be on the order of n, and then when you do that, you need to compute the number of large eigenvalues. So what you do is compute the Frobenius norm of the matrix. So that's the sum of the squares of the eigenvalues, and then it will work out. Yeah. that's just an application. And then you could imagine, maybe lots of polynomial time approximation schemes could be strengthened into results about sampling the Gibbs measure. So that's kind of an interesting thing to think about. Okay, so that's all I want to say. So in conclusion, we have this new algorithm. We can sample from this large class of models. Has a lot of applications. So for example, maybe you wanted to sample from the Ising model, but it's on an expander graph. You can get much better results than were previously known if you're willing to use this method. Here are a bunch of other applications. So contextual stochastic block model. This is a version of block model where you have side information. In a certain regime of parameters, we can sample from the posterior in this model. There's lots of hard open questions, like getting it in the full regime that it should work. And that's probably a pretty difficult and exciting open problem. Okay? Okay, other takeaways, variational inference. It's good to know about this because that's actually how we can predict which problems should be tractable, or statistical physics, whatever you like to call it. And an interesting question, again, is what aspects of the whole story I told you extend beyond the Ising model. So a lot of things in the world probably do decompose into mixtures of nice things, and maybe we can sample from them using this fact. But of course, the proofs are all for Ising model. Okay, so that's all I want to say, and thanks for listening.
So for other CSPs, like where there are p-tosses in the dense case,
we don't know how to sample, yeah.
Because of the fact that like this is for Ising.
Exactly, yes. That's open question.
So related to that, like, is there any like candidate something that's like sort of smells like Ising but a bit different that you would get if you were to try to trace back?
So for example, the mean field when I told you about, there's like mixture of product measures, this is actually true for a whole class of functions which have like small Gaussian widths of the gradients or something. And the fact about Ising models is really just a special case of that. So you could imagine that there's many other types of functions which satisfy that property, and perhaps we can sample from them, but we don't know.